All right, guys, we're going to go over heating curves today. So heating curves show you phase changes of a substance. So this heating curve is going to be for water. So you might want to jot this down. So you should have printed these out, these skeleton notes out that you can write on. And within the curve, it's going to show as you add in heat over time, how the temperature changes, and then how the phases change. So we know we have solid, liquid, and gas. So we're going to label where those phases are in this heating curve. So at very low temperatures, we're talking way over here on the lower left. We're at very low temperatures. We are going to have a solid. So down here, this will be our solid. Where it starts to flatline. So as you're adding in heat, those solid particles are gaining energy. They're increasing their kinetic energy. They're starting to move and vibrate a little bit more. And they're starting to possibly getting close to breaking their bonds. So this is where you start to flatline. At this flatline is where a phase change is happening. So the solid is turning into a liquid. And we know that that's called melting. So I'll just write melt in this direction. And if we were to go reverse, rather than putting heat in, we take heat out. We can go from a liquid back to a solid, and that's called freezing, right? So we know that. So we'll just write freeze here. And again, that's going in the reverse of the melting. Now, in case you don't know this, solid ice and liquid water they melt and freeze at the same temperature. So that is 0 degrees Celsius. So over here on the side, this is going to be 0. Now, once all the solid will stay at 0 degrees Celsius until it is completely melted into a liquid. And then the temperature starts to rise. So we have an increase here. So this right here, where we have this is going to be our increase in temperature. That is all liquid. And then we encounter another flat line. That means another phase change is taking place. That's a liquid turning into a gas. That's called vaporization or vaporize. And again, that's adding heat. So we're going in the forward direction. If I went in reverse and taking heat away, gas going to a liquid, that's called condensation or condense. And that's the reverse. So condensation, reverse of vaporization. And another term for vaporization is boiling or evaporation. But vaporization means just a liquid going to a gas. So this happens at 100 degrees Celsius for water. Again, this is for water. And then once all of that liquid, again, it stays at that 100 degrees Celsius until all the liquid is turned to a gas. And then those gas particles, again, gain all that energy. And so their temperature starts to rise. So up here, this is all gas in this location. So you can see there's actually 5 different parts on this graph. And we can use this graph to help us figure out what formulas we need to use to figure out how much heat we need to add in to change the temperature of water and change their phases. So we're going to number the different parts. Down here where the solid is, we're going to call this 1. Where melting and freezing happening, that's going to be called 2. Where liquid is, this is called 3. Liquid going to a gas, vaporizing, that's going to be 4. And then where we have just gas, this is going to be 5. All right. So we're going to identify the different parts and what to use. So on part 1, 3, and 5, you can see that's where we have a temperature change because the graph is increasing or decreasing. There's no flat line on 1, 3, and 5. So when you have 1, 3, or you're in 5, in that position or in that area of the graph, you're going to use Q equals MCAT, the specific heat formula. So M, C, triangle T. So remember, Q is your heat, M is your mass, C is representing the heat, the specific heat of that substance, which happens to be water, and then delta T, change in temperature. Okay, 2 and 4 are some new things we haven't talked about. So you can see on 2 and 4, flat line, right? No temperature change. We cannot use MCAT here because if you said there was no change in temperature, that means there's no heat. We know there has to be energy in there to break those intermolecular forces of the solid to go to a liquid and then a liquid going to a gas. So energy has to be going in. So instead of using MCAT, we have to use something different. It's called latent heat. So for position 2, we're going to use something called molar heat of fusion. Try to squeeze this in here. Okay, and the symbol for this is triangle H, which is delta H, and then FUS. Oh my goodness, so sorry. I need to go back, not where I want to go. Get these messages here. Okay, so molar heat of fusion, delta H fusion. So for water, so you need to write this down. For water, the molar heat of fusion is 334 joules for every gram of water that you have. Now, you can use, again, there's all kinds of charts you can look up, right? Another molar heat of fusion for water is in terms of moles. And so that one, that's all right, or you can use 6.02 kilojoules per mole. So that's kilojoules per mole. So we have per gram or per mole. Most of the time we're just use the per gram, so it's the easiest one to use. Okay, then position 4. I'm going to write it over here so I have more room. Position 4. Another latent heat. Again, this one's called molar heat, but of vaporization. All right, so the notation for this, the symbol for this is triangle H. Triangle H means heat. In other words, enthalpy. It's called enthalpy, but it means heat. Okay, and then VAP for vaporization. And I'm going to write down below here what the values are for water. So again, this is for water, you guys. So the joules per gram is 2,260 joules for every gram of water you have. Or if you want moles, you can use 40.7 kilojoules per mole. All right. Last thing I want to identify on this graph is which way is endothermic, which way is exothermic. So endothermic, it means we have to add heat in. So adding heat into like an ice cube will help melt it. Adding in heat to a liquid will help vaporize it. So going up the chart in this direction, this is all endothermic. You have to put heat in to get that phase to change. Okay, the other way, let's say we're going this way, going down backwards. So going from a gas to a liquid or a liquid back to a solid, that's exothermic. So like taking liquid water and freezing it is exothermic process because you've got to get that heat out of the liquid so the liquid can go into the solid form. All right, now, so we're going to do a problem using all this information off this chart to calculate how much heat either going in or going out of whatever system we're looking at. So let's look at that sample problem that's on the bottom of your skeleton notes. Here it is. They want to know how much energy is needed to melt 10 grams of ice at 0 degrees Celsius. So we're starting at 0 degrees Celsius, all solid ice, and we're trying to raise it to a temperature of 25 degrees Celsius. So let's mark it on the graph. Let's go back. I'll use green here. So we're starting at 0, and it's all solid. So we're starting like at this point right here, right at this little point here at the start when it just starting to melt. Now, we've got to get this ice to melt. So it has to go all the way through part 2 just to get all the solid to go to a liquid. Now, once it turns to a liquid, it's still at 0 degrees Celsius. The final thing is I've got to get it up to 25 degrees Celsius. So let's say like 25 degrees Celsius is right here. So I'll just write 25 degrees Celsius. So I've got to get it from 0 up to 25. So there's two calculations that I have to do. So let's do the melting part first. Melting, we're going to use this molar heat of fusion to first figure that out. So let's go over here. We're going to write out the formula for this. So we're going to do Q. So this is for part 2 on the graph. That's the flat line. We're not using MCAT. We're going to take the mass of the substance and we're going to multiply it by the delta H fusion. All right, so and I plug this in. It's going to be 10 grams. Whoops. 10 grams of ice. That's what they told me. And then I'm going to use that molar heat of fusion from the graph. So if you look at your graph, again, it is 334 joules for every gram of water I have. Okay, grams are going to cancel out, right? So I'm left with joules. So this is going to give me 3,340 joules just to melt the ice. So again, that's just going across, taking the solid, going to a liquid. Number 3, we're going to do the third part. Again, that is going from 0 up to 25 degrees Celsius on that chart. We're going to use MCAT. So Q equals M, C, triangle T. So I'm going to plug in my values. I have 10 grams of liquid water now. Specific heat of water. I gave that to you in your notes from last time. That is that 4.184 joules per gram degrees Celsius. And then change in temperature. So I'm going from 0 up to 25. Final minus initial. So 25 minus 0 degrees Celsius. That's going to give us 25. So I multiply 10 times the specific heat times 25. That's going to give me a value just for part 3, 1,046 joules. So I'll just say it's 1,046 joules. Now I have to combine these two together. I've got to add this down here. So I'm going to add the 3,340 because I'm trying to get the total amount of energy to melt it. So again, this is for melting. And then I want to know how much energy to get it up to 25 degrees Celsius. So I have to add it to the 1,046. So the total, adding these together, is going to be 4,386 joules. All right, guys, so now you're going to do your assignment and work on some of those problems. Again, keep your skeleton notes out of your heating curve. Figure out where you're starting on the curve and where you need to go to and what formulas you need to use.